Okay, so I'm recording this class. This relates to MATLAB assignment number 2, the second exercise. Second exercise says you can get an idea of how flops are related to actual computing time by using the MATLAB functions tick and tock, which measure the elapsed time between the invoking of tick and the invoking of tock. Okay, so like for instance, here in this sample MATLAB code, you have a matrix A. It's creating a matrix A and a matrix B. The dimensions are 1,000 by 1,000. Okay, the dimensions are 1,000 by 1,000. So they're big matrices. Okay, 1,000 rows, 1,000 columns, and the matrix multiplication, MATLAB will do it, but it might take half a second, who knows? But tick tock will tell you the time it takes to multiply A times B. All right, now, so there's a lot of flops involved. Flops are mathematical operations. And if you try this several times, this command, you'll see there's a lot of variation in the reported time. There are many variables that affect this time: processor speed, memory, number of open applications, operating system, to name a few. So this is one of the reasons for using machine independent measure like flops. So what you're going to be doing in this problem when you do this, okay, there's code here. There's code, and this code is going to measure the time it takes. Well, there's a loop here. You see this? You see this? I don't know if you've seen how many have seen like for loops, do loops in programming. Okay, Marcella has, and so this is a for loop. Belen has, wonderful. So you see, you're letting X go from 3,000 to 8,000 with a skip factor of 1,000. So that means MATLAB's going to generate, okay, Jacob, very good. Jacob, stay in the room, okay? I was calling you earlier. Don't leave, okay? Don't leave. Good. I'm glad you're with us. Like 3,000 by 3,000. Okay, all right, okay, thank you, that's okay. And then 4,000 by 4,000, see it's skipping by 1,000. And it's gonna do finally 8,000 by 8,000. Let me see here. So there's gonna be 5 matrices. Hold on. No, 6 matrices, and the matrices are getting larger and larger. Now, what are you doing with the matrix? You're doing an LU factorization. MATLAB's going to do an LU factorization, and it's doing the products of the diagonal entries. Effectively, right, that's like computing the what? What is the product of the diagonal entries of U? That's almost like computing the what of the matrix A. Do you remember? That's right, Mikhail, the determinant. The only thing that's being left out is the -1 raised to the power, dealing with the number of row interchanges in the permutation matrix. Okay? But effectively, you're computing, for all intents and purposes, multiples of determinants. Okay, you're computing essentially determinant-like numbers for these matrices, and they're getting bigger and bigger. And what's going to happen is, as you're going to be recording the times, but then you're going to be plotting. You're going to be plotting as well. You want to record the times and then plot the times. That's what this plot command's for here. But then you're going to say, hold on, because you want to relate the number of flops, the number of mathematical operations in computing the determinant, to the time data. Okay, and we've seen that the number of flops for computing the determinant this way is approximately 2n cubed divided by 3. 2n cubed divided by 3. If you, hold on here. Now, let me just see here. Yeah, let me show you where that is. One moment. Okay, I have it here. Let me just bring it up. Okay, so this is a numerical note from section 3.2, and you'll notice this piece of information here that so section 3.2 is where you were using properties to compute determinants, and that's how you came up with the fact that the determinant of a matrix A is equal to -1 to the rth power, where r is the number of row interchanges in the permutation matrix, times the product of the pivots in the echelon form of the matrix U. Okay, so it can be shown that evaluation of determinant using the row operations, so you can use the properties of determinants, requires about 2n cubed over 3 mathematical arithmetic operations, or 2n cubed over 3 flops. Okay, one moment. Okay, thank you. That was my brother, but I told him I'm teaching my class. So, all right. So the number of arithmetic operations or flops is 2n cubed over 3 if you use the properties of determinants, which you are doing with MATLAB assignment number 2, exercise 2. So now, if we go back to the problem here, or the exercise, here's where we were, okay, and they're creating code that's going to allow you to study the plots that relate to the flops, and the plot that relates to the times it takes to compute these determinants. And you should have basically 2 graphs that are parallel to each other. They won't be perfectly parallel, but they will be reasonably parallel. And that's what this code's going to do. Okay, because this code here it creates basically a proportionality. This T1 over Y1 creates a proportionality between the time data and the flop data. So the code's given to you, but when you run this code, and I want you in your output, when you submit your MATLAB assignment number 2, the work, the code, I need to see this code and then the output produced by the code, right? When you produce it, you should get a plot, and you're going to print the graph with both plots. You're going to include that in your output and label the plot that's for the flop graph. You're going to have a time graph and a flop graph. Okay, and they should coincide with each other. The more flops it takes to compute a determinant, the more time it's going to take. Okay, and you're computing determinants of of increasing sizes. Okay, the smallest size is 3,000 by 3,000. 3,000 rows, 3,000 columns. The largest matrix has 8,000 rows, 8,000 columns. So when you do this problem, you want to make sure you have all of, don't have anything else running on your computer don't have the internet on, don't have, don't be playing video games. Just strictly run this code on your computer so you can get an accurate graph. Because if you have other stuff running, it'll cause the graphs to be a little bit distorted. I mean, or it just your result won't look right. It won't. It would look not good because you know it's going to take more time to produce to get the determinants if you have if you're playing video games or you're on the internet on the computer, right? So just make sure everything's off except MATLAB. All right, when you run this code. And again, you're going to print the graph with both plots, and you have to label the plot of the curve 2n cubed over 3. That would be the curve that corresponds to the number of flops. And n's going to go from 3,000 to 4,000 to 5,000 to 6,000 to 7,000 to 8,000. That should be your your axis, right? Goes from, I mean, well, yeah. I mean, you know what I'm trying to say. The determinants are 3,000 by 3. Well, it's a determinant of a 3,000 by 3,000 matrix and a 4,000 by 4,000 matrix, and so forth, up to an 8,000 by 8,000 matrix. So n is going to, an n by n determinant. N's going to go from 3,000 to 4,000 to 5,000 to 6,000 to 7,000 to 8,000. Okay, and so it's a really cool exercise, and you'd be surprised. It could take a little time to compute those determinants. So I've had students a long time ago do this, and this is maybe 10 years ago, and some of them, their computers crashed doing this because their computers weren't, they were like, 10-year-old computers, and you need to have memory, you need to have computing power to do this. These are big determinants, but you'll have a lot of fun with it. Are there any questions on this second MATLAB exercise? For MATLAB assignment number 2? I don't think, Jacob, it would be an issue for today's computers. I do not. But like, even today's computers, computing a determinant of a 3,000 by 3,000 matrix still could take some time. I mean, I doubt it could still take a little time. And that's the purpose of the exercise, to sort of explore. Mikhail, the lines will not match the two graphs, one for the flops and one for the time data, won't match perfectly, but you want them to be, you want them to at least see, you want to see like that the graphs are parallel, because the larger the determinant is, the more time it should take to compute the determinant. But to have the most accurate reading, you just don't want other programs running in the background while you have this program running in MATLAB on your computer. Well, so Mikhail, that's interesting. I think maybe when you talk to your group members, see what they get. Maybe there's a reason why your graph runs parallel for the most part, but then it switches somewhere in the middle. That's interesting. I'm curious if maybe what's going on there. That's something to talk about with your group members, okay, and see if they get that kind of result. That's why it's great to work in groups. But I have heard that kind of thing, Mikhail, before. But yeah, that's right. You should say, why is it doing that? Because ideally it shouldn't, right? So, okay, excellent. Are there any other good questions? Okay, so once again, this was MATLAB assignment number 2, the second exercise at the top. And I'm going to make sure this recording goes into where MATLAB assignment 2 is posted in Blackboard. Excellent.